like to continue with my second part, and just to repeat, a lot of the INSAR theory principles is already online, and I already gave you the link to that if you're interested. I think also one of my predecessors in this lecture series discussed that. So I would like to discuss some things which are maybe a bit more new. Let me look at this. So, and I would like to talk about the geometry of INSAR now. And here I will go a little bit more in depth. So the previous lecture was a bit more on a higher abstraction level. Here we go a bit more in the equations. But also I try to come up with some new things. So INSAR geometric projection and decomposition. That is what I will talk about, the geometry of the whole thing. Now, why are we doing this? Well, because in many cases, INSAR geometry seems trivial. We're looking from a certain direction. We have line of sight motion, but actually it's a bit tricky. And what you see if you look at literature is that there are many cases because the complexity is underestimated, the errors are being made. And that leads to errors in the interpretation. Let me show you a couple of statements that you can find in literature, and this is just as an example, and not to blame anybody, or because I made many mistakes myself as well, but just to make the point clear. So, for example, in the upper left, the talk it's about vertical displacement in a certain region by a certain method using the available data described here. So basically, this was only one viewing geometry. So we have line of sight deformation, and it is claimed that vertical displacements were found or reported. That is not possible. It's not possible to do that unless you make assumptions, which you then need to make clear. But the reason that it's not possible is that we're viewing the Earth under a certain angle. We're not looking downward with INSAR, we're looking under an angle. So we don't know in which direction the motion takes place. As long as it is a motion difference or a position difference in the line of sight to the satellite, then we will observe it. But we cannot say whether it's vertical or horizontal by definition. Here in the second one, we constrain the shape of the magma chamber by reconstructing the vertical and horizontal components of the surface displacement using two interferograms. So in principle, vertical and horizontal are two words, but obviously vertical is one direction and horizontal is a two-dimensional plane. So it is actually two parameters, east and north. Negative east is west, negative north is south. So in principle, if you would have only two viewing geometries, you cannot reconstruct vertical and horizontal. You can do something. I will discuss that in a minute, but you cannot simply say, well, we're just deriving this. In the upper right, select consecutive pairs was converted from SAR line of sight to vertical displacement using this equation, which is written over here. Now, converted would mean that it is possible to go from a certain line of sight to the vertical, and it's not possible. It is an impossibility. What you can do is you can project it, but that is something else than converting it. And this is not just nitpicking on words, but it is very important because it's a totally different parameter. Here we have another one where we say, as a result, the north component is insensitive. We can only measure horizontal motion along the east-west axis. So therefore, we add the constraint that the north-south motion is assumed to be zero. Now, these are basically two errors on top of each other, right? One, it's true that there is less sensitivity to the north component, but that doesn't mean that you cannot observe it. Whether you can observe it depends on the signal-to-noise ratio, and it depends on the size of the signal. So that is in the signal-to-noise ratio, actually. So if I have my measurement precision is high enough and the signal is strong enough, I will also measure the north component. So we will see it's not actually the north, it's a little bit different. But the second thing is actually more important than if you say it's insensitive, you cannot therefore conclude that the north-south motion is assumed to be zero. These are two different things. So one describes the observation system, the other describes the physical mechanism or the physical thing that you're trying to observe on planet Earth. To the measurements along vertical east-west, I'll not dwell too long. If you have 2 sets of INSAR images available, to successfully estimate the vertical and west-east component. So I think these are typical statements that we encounter quite a lot. Now we kind of analyze that a little bit and try to make a categorization of, okay, what is, in our opinion, the problem here? And we come up with 2 types of errors or problems. One is what we call the projection error. And the projection error is defined as projecting a line of sight displacement estimate onto the vertical and presenting this as a vertical displacement. It was the example that I showed you before here, also converted from the line of sight to the vertical using this equation. In case of vertical motion, one fringe is associated with 3 centimeters of motion, as the incidence is 23 degrees. The line of sight can be transformed into the required direction. So this all seems to suggest it's just mathematics or just an equation, and we can then do this. This is a problem because the projection is something else than the conversion. So I will show that here. So, but also you can see it in figures many times. So here we see, for example, DINSAR vertical displacement indicated from one viewing geometry. This is from the same paper, I think. And the problem is actually that the equation that is stated here is incorrect. So if we have our line of sight statement and we divide by cosine theta, then what we achieve is the projection of that displacement onto the vertical. But the projection onto the vertical is not the same as the vertical displacement. It is something completely different, right? It would be the same if we would know by some reason that there cannot be any horizontal motion, or if we explicitly say, well, we assume that there is no horizontal motion, then the projected displacement and the vertical displacement would be the same. But in general, you cannot say that. And I think it's important to keep that in mind with studies. So this is a projection error. The other one is maybe more important and a little bit more difficult. This is what we call the decomposition error. And if you write it mathematically, basically we're ignoring the null space in the 3-dimensional solution space using only 1 or 2 viewing geometries, for example, ascending and descending. Now, statements that you see here is that if you have 2 data sets of INSAR images available, then we can estimate the vertical and east-west or west-east components, or that it is possible to disentangle east-west from vertical, or that we can reconstruct vertical and horizontal from the 2 interferograms, that we can estimate them. So basically, these are all statements where a rather easy step is made. I think in many cases people know, but actually the message that is broadcasted to people who are maybe not so into INSAR is actually wrong in my perspective. Okay, what is let's dive into this problem. So in reality, we of course, if we're on the planet and we have displacement or motion of an object, it always occurs in 3-dimensional. So we have an east, north, and up component. And it's east, north, up, not northeast, up in this order, because we're talking about a right-handed Cartesian reference system. So X, Y, Z is also in a particular order. So it is east, north, up, which is not the same as northeast, up. That would be a different frame. So this is what we're talking about. So for example, if we have a landslide here, as you can see over here, then the motion happens in the 3-dimensional world. But what we can do is we can come up with an alternative coordinate system. And we call that coordinate system TLN, so transversal, longitudinal, and normal, where transversal is related in this case to the slope, longitudinal is in this case related to the ISO elevation line, or the ISO, in this case, the street, for example, and the normal would be orthogonal to that. Now, if you would have a real vertical, or if you would have a displacement, a subsidence ball, for example, this is what you see on the right-hand side, And here we see the displacement that is happening. And actually what will be happening at these balls is that there is horizontal motion at the top. At the sides, there will be horizontal motion pointed inward. If there's inflation, they will be pointing outward, but basically here this is pointing inward. And if you would look at a cross section, this is what you would see. So the actual motion, the trajectory of a particular point on Earth in a Lagrangian sense will follow the black lines over here. So that means that they correspond with a vertical component, and in blue here, the horizontal component. So this is where you see that the blue vectors are pointing inward. So a typical INSAR product looks like this, colored dots, displacements in millimeters per year, and this is what we're dealing with. Now we need to know in which direction this displacement takes place. And as I already indicated, we start with the line of sight. So the real world displacement in the east-north up component here on the left-hand side relates to the line of sight motion on the right-hand side. So we go from 3 dimensions to 1 dimension. Now on the right you see the picture. So we have east-north up coordinate system. We have a satellite viewing in a certain direction. We have an arbitrary displacement vector d. E and u is east-north up with an east component, a north component, and an up component. And what I'm measuring is the projection of that displacement onto the line of sight to the radar. And what is very important also is that this has to be seen from the perspective of the target and not the perspective of the satellite in the space. And we will see that this has a big difference. So what does it look like if you look at this in space, in the 3-dimensional space? Well, actually it looks like this. So the satellites are flying around here in a descending orbit and an ascending orbit. These ones are right-looking. Most of the satellites that we have now are right-looking mostly. ISRO will be left-looking. It will be interesting. But if you have a right-looking system, it looks like this. So the satellite is flying here. This would be the line, nadir line down, and looking under a certain angle to the point where we're interested in. Now, this triangle here defines a plane, which we call the zero Doppler plane, that is orthogonal to the direction of motion of the sensor. And what we typically do in current SAR focusing is that we're focusing on the zero Doppler plane. So that means that every position will be focused as seen orthogonal to the orbit. Well, we have that for the ascending orbit, we have it for the descending orbit. And these two planes interact with each other. Then there are a couple of angles. One is the incidence angle. So if we look at only here at the descending orbit, then you see if we go further away from near range to far range, then the incidence angle will change. So basically the incidence angle is dependent on where I am in the image. The other angle, which we often talk about, is the heading angle of the satellite. But I will show you in a minute that that is actually incorrect. But if you look at the satellite perspective, we have the northeast axis over here. Satellite is in a descending orbit, and the heading in this case would be maybe 190 degrees or so. So heading a little bit west to west-southwest. Southwest-south, I should say here. The point is that if we are on Earth and we're looking at a sphere, then as you know, the meridians that you see over here, they are not parallel. They converge to the North Pole, and there they meet each other. So if in this perspective, it means that the north direction here results in a different angle for near range than for mid range and for far range. And on the left-hand side of this figure, you see a top view of that. So in near range, the heading of the satellite would be indicated over here, but if I'm further away from near range to far range, you can see that the angle that I'm actually dealing with is alpha d. That is decreasing as I go further away from the nadir. So we should not talk about the heading angle, but we should talk about the azimuth of the zero Doppler plane. This is the thing that is important. So the heading is only important if you look at it from the perspective of the satellite. If you look at it from the perspective of the target, it has to be the azimuth of the zero Doppler plane. So basically we have two angles, the incidence angle and the azimuth of the zero Doppler plane. They matter. Now if we take it from there and we bring it to the line of sight mapping. So first of all, we have a displacement in the east-north up and on the Earth. We have a line of sight direction with the azimuth of the zero Doppler plane, alpha d, and incidence angle theta, local incidence angle. And basically what we're observing is the line of sight, the projection of the displacement onto the line of sight. And that is indicated here in red. That vector is in the zero Doppler plane. That's what you can see over here. Okay, so this is the geometry that we have if we have only one viewing geometry. Now, what does it look like if we write it in equations, in mathematical equations? So we have the three-dimensional displacement here in blue and the one-dimensional line of sight observation. So basically the equation goes from here on the right-hand side, the east-north up, the three components of the displacement vector, and on the left-hand side, the observation, which is one-dimensional line of sight. And in between, the projection, it's a projector, so two angles, theta, here, here, and here, and the azimuth of the zero Doppler plane, alpha d, over here. And then with cosines and sines, I can have this projection. Now, the consequence of this, that I have one observations and three unknowns, is that there is a null space with dimension 2. And that actually looks like a plane. This is a bit difficult to visualize in 3 dimensions, but basically you have the red line of sight vector. If you see my finger in the camera over here, then the plane is, let's say, orthogonal to that line of sight. So that is the blue plane. We call it the null space or the solution plane. And it means that any kind of displacement vector in that blue plane will result in the same observation. So we cannot distinguish that. This is why it's the null space. Okay, so this is a problem because we have 3 unknowns, east, north, up, and we have one observation. So at the very least, ideally we would like to get to many different viewing geometries. So if we would have 3 satellites viewing under different angles, then we have still one 3-dimensional observation parameter vector, east, north, up of the displacement. But now on the left-hand side, we have 3, 4, maybe even more observations of that same object. So this would be basically the ideal case. Now, this is not so easy because what you see here in green, RUM or RUM, this is our abbreviation for a region of uniform motion. So basically, when we look at the Earth, we would like to see, we would like to ensure that scatterers from descending and ascending and different viewing geometries are actually from the same area that we can assume to move as a whole. So region of uniform motion means that within that region, within that green box here, there is no internal motion. Everything moves as a whole. And only if I have a region of uniform motion and I have more scatterers from different viewing geometries, then I can do something with these equations over here. Okay, now we first want to have a look at the case in which we usually have, that is that we have typically only 2 viewing geometries, an ascending and a descending image. Sometimes we have 2 ascending and 2 descending, depending on the latitude where we are, but actually the angular differences are very, very small. So it makes sense to look at this as this problem. So here we have still on the right-hand side the displacement vector, east, north, up. On the left-hand side, we have 2 observations. So we still have an underdetermined problem, and the null space is now one-dimensional. Previously, it was the plane. Now it is actually a line, as we will see. Now, what will that line look like? So first of all, here we see the line of sight motion for the ascending orbit and the descending orbit. We have the 2 zero Doppler planes, and they intersect here. And let's see what that looks like. So if we have only one viewing geometry, this is a repetition of the previous graph. We have a line of sight motion in green, and the null space is the green area over here. Now, if we have 2, also have, for example, an ascending orbit that may observe the blue line of sight vector, and orthogonal to the blue line of sight vector is also a plane, two-dimensional plane. Now the point is that these two planes will intersect, and the intersection will be a line, and this is what we call the null line. And the null line is a concept that has not been discussed much in literature, but this is an important parameter for a particular mission. So also for ISAR, we will be able to compute the null line for different locations on Earth. And it will be different because it is a left-looking sensor. So if we have a line, then basically we can describe that line by only two angles, which is the azimuth angle and the elevation angle. So the azimuth angle is what you see down here in the east-north plane, the dashed, sorry, I have to point here, the east-north direction, so the dashed line or in orange here, that is the azimuth angle, theta, and the elevation angle is seen here in the north-up plane as, you know, how steep the null line is. So these two parameters describe the null line. So if we have this situation, an ascending and a descending image, we still have an underdetermined problem, and there is an infinite amount of solutions, but all these solutions are along the null line, are somewhere along the null line, described with these two angles. Okay, so now the question is, what are we going to do now? Now, there is a conventional approach that is basically most of the literature that I was showing earlier, where people would say, well, we just ignore the north because we know that the satellites are less sensitive there, or the arguments that you just saw, and we just look at east and up. Then you solve the underdeterminacy problem, because you have two unknowns on the right-hand side here, and you have two observations on the left-hand side. However, this gives you a decomposition error. And in order to understand that, I try to make that clear here in the figures. So actually every point here on this null line would result in a different result, in a different parameter that is estimated, and this will be biased. Okay, let's have a look here. This is just an example for the decomposition error. So if we would do this and only compute the east-west component, like in many cases it is done. So here we have this subsidence bowl. You can see this a little bit where we have the location where we have hard infrastructure. We get a good estimate of displacement rate. And obviously the displacements are also in the north-south direction. But here we only see the east-west direction. So the question is there now a solution to this problem? And actually there are two solutions that I would like to discuss. One is a little bit more eccentric, but I think very fundamentally correct. The other one is actually very practical. So instead of having the east-north-up plane, we could also, this is for the east-north-up coordinate system, we could also define a new coordinate system, and we call that the NLA coordinate system, and the NLA stands for null line aligned reference frame. But actually it has, the NLA also stands for the null line, the leaning axis, and the azimuth axis over here. Okay, so let's look at the problem here. So if we would do it in the east-up plane, this would be what is often done, then basically any motion here along the null line, which we cannot observe, would result in a projection onto that east-up plane. So this projection K, and we would not know which error we would make. It would be strongly biased the up component, but it would also bias the east component in this case. So only in the case when the azimuth of the null line is 0, then we only have a bias in the vertical component, in the up component, and not in the east. I will show you in a minute where on Earth these cases happen. So what you could also do is you could say, well, instead of having a plane in this east-up plane, we can also have a coordinate system which has the null line as one of the axes, we have two other axes on top of that, the leaning axis and the azimuth axis. So in that case, this orange plane actually is an unbiased plane, because any motion or any position along the null line would all project to the same location in this NLA plane. So in other words, whereas on the left-hand side we make an error, we have a bias, this vector k. If we choose a different coordinate system, which is very easy to do because we know the orientation of the null line, then we don't have that bias, and we get estimates along the A and the L axis. Okay, so as in writing here, an orthogonal projection of any displacement vector onto the NLA plane will not influence or bias the two in-plane components. So the null line, N is the null line axis, L is the leading axis tilted backward with an elevation, A is the azimuth axis, which is horizontal with a certain azimuth. So the definition is in the paper that I will refer later. Okay, so how big is this problem? Is this really a big problem? Well, if we want to say that, actually there are only two parameters which are important. That is this orientation parameters of the null line. So let's have a look at that here. So what you see here in the middle graph is the azimuth angle of the null line. So how far off north is it in degrees? And here you see basically the Earth as we can observe it, a certain area, doesn't matter, the longitude doesn't matter, but what we see is that for the northern hemisphere, I think this is for Sentinel-1, yeah, this is Sentinel-1, the northern hemisphere is more or less greenish over here. So actually, most of it is, the null line is indeed in the north direction with a certain tilt. That means that the bias will be almost completely in the vertical. So if we do this east up projection, what is typically in literature, then we will bias our up component. We'll get the wrong estimate. In the southern hemisphere, you see that this pattern changes depending on where you are in the swath, but you can see that it goes up to maybe 4 degrees or so. So there actually we will also influence the east component. It will be biased. If you look at the elevation angle, there obviously this is always a bit positive because the orbits are not over the pole. And here the values are basically around 10 degrees or so. So let's go to the take-home message. So if you choose for this, I told you there are two possibilities. This is a possibility one. If we choose to go from this null line aligned reference frame, that means that if we have only ascending and descending data, that if we choose to have the east up plane, it's biased. If we project on the NLA plane, it's unbiased. So it makes a lot of sense to do this. Now, when should you do that? Well, if you would like to, for example, do modeling with it, if you're interested in seismic signals or geophysical signals or mining or all these kind of things, you would like to build a model, then it's obviously much better to have unbiased data than to have biased data. And it's just a different coordinate system. So it's a different choice, and you get rid of the bias problem. It's also uniquely interpretable, it's unbiased. The negative side of it is, of course, that it is less intuitive. So if your goal is to inform the entire world, or if anybody should be able to understand it, or you don't need expert interpretation, then obviously it's less intuitive because we have motion in these two directions, which are not the primary wind directions. Now, obviously for the traditional choice that is usually made in the east up plane, so we have an east-west component and an up-down component, that has the advantage that it's intuitive because we more or less feel where east is, we can interpret that, we know what up is, but it is wrong, it's biased. How wrong it is, that depends on the particular location and what you want to do, so you cannot make a general statement on that. So also, I think just to wave it away as just this is nitpicking would be wrong, because in a generic sense, if the impact is big, of course the bias effect is also big. So this is one approach. Then the other approach is maybe a little bit more practical for those of you who are interested in that, and that is another coordinate system, which we call the TLN frame. and that relates to transversal, longitudinal, and normal. And here, this goes back to a presentation or the work from Ling Chang already a while ago, where we look at line infrastructure like a road that you can see over here. Now that road has a certain orientation. The roads don't all only go to the north, they go in different directions. So we have an angle, capital lambda over here, and it has a tilt, so it may go up or may go down, and it may have also tilt in the east direction, so a cant as we call it. So basically we have three angles, lambda, omega, and capital phi. Now, what you can in these cases do is that if you know that you're interested in line infrastructure like this, then the likelihood that this road will start moving in its longitudinal direction is actually quite low, right? It's not zero. It depends on the situation. So we still need to keep on thinking. So, for example, if the road is going straight down, right, then it may actually move in the longitudinal direction. You may want to make a different choice. But the message here is that in many cases, we know something about what we're doing. We don't want to focus on application agnostic processing, as I showed you in my first half of the lecture. We know that we're interested in the road. We know that there may be some concern. We may be interested in a landslide, as you can see over here. And then we know that the landslide will not move up the mountain, and most likely it will also not move in the longitudinal direction. Most likely gravity and the plane of the mountain will be more or less the direction in which it will move. And I don't need to know it exactly. What I need to know is that the longitudinal component is very close to zero. And I don't need to make an assumption that it has to be actually zero. I can actually introduce my uncertainty also in my equations, as I will show you in a minute. So here on the lower right picture, you see a sketch of a mountain and the angles that we define for the longitudinal direction, which are parallel to the ISO height lines, the transversal direction, and the normal direction. Now, another example here, this is another sketch with a top view and a side view. So if you have, for example, a subsidence bowl, right? The ground is going down, this is indicating by the minus sign over here, then the longitudinal direction is equal to the ISO deformation lines, which are the lines that you see here, the circular lines. So lines of equal deformation. Transversal is towards the center of the subsidence, and normal is orthogonal to it. You can see that in the side view over here. So what is the key thing? So if you define a coordinate system like this, then east, north, up is the same everywhere in your image, right? The north is everywhere the same. But if we define this system, then at every location, we have a different orientation of the coordinate system. And we call this a strap-down approach. Just as a background, the strap-down terminology comes from inertial navigation, where we have a sensor on a car, for example, and the car changes position. So there also the coordinate system changes all the time. So we call this a strap-down approach. Now, the consequence of this is that the longitudinal displacements are assumed to be zero. And again, with uncertainty that I will express in a minute. Now, then we can do basically the same thing as I showed you before with my objections for east and north, but now in this equation where we have two observations on the left-hand side, ascending and descending, and we have two unknowns, the transversal and the normal components. And then with the projection, I can perfectly estimate that. There's no problem here. So basically, I'm ignoring the longitudinal component. And my argument is that it is much more physically meaningful to say that the longitudinal component is expected to be zero than that the north component is expected to be zero. The north component expected to be zero would mean that somehow in nature, objects have the tendency not to move in the north direction, but only in the east direction. And that obviously is nonsense. So this is physically more meaningful. Now, okay, what is the problem here? So this only works if we have this orientation of this frame correctly. If we have it incorrect, or if it is tilted or whatever, then we're again introducing a bias, similar like we did for the east-up decomposition. Now here is the set of equations for this, and just to show you a little bit how we do it, we'll not go too deep. So basically we have the transversal and the normal components over here, and the lower part of this set of equations actually has this orientation of the strap down coordinate system at every location. And what you see is that what we need are pseudo observations, as we call it. So we need, from the context, we need to have a first approximation of those angles. These are indicated over here. They're also the unknowns that we're trying to estimate. On the right-hand side of this slide, you see the stochastic model. The D stands for the dispersion, so the variance, if you like, or the variance-covariance matrix in this whole thing on the right. And here we have the precision with which we know this orientation of the coordinate system. So what you need to do is, in the cases where you're not so sure about the orientation of the coordinate system, then these values have to be higher. So you have a bigger variance or a bigger standard deviation. You don't know the angles that well. But if you're dealing with a case, a AAA case, you know the application, you're aware of it, and you're aligning it to it, then actually these numbers would probably be smaller. And that way we can introduce the uncertainty in our estimation problem. So the uncertainty of the alignment is here in this set of equations. Now, what do we get if we do this? And this is very interesting. So we get an estimate like this, where we have a north axis here and the east axis over here. We have this gray area is a region of uniform motion. So we assume that this whole area moves as a whole. So if it's a landslide, for example, it's maybe an area of 30 by 30 meters, or if it is some particular object on a slope, then we could define that object. So this depends on the context. But we're estimating the longitudinal and the transversal, the normal and the transversal component. But because we have this uncertainty in the orientation of the frame, we also have an uncertainty in the longitudinal component. So the longitudinal component is 0, right, by definition, because this is how we define the frame. But there is uncertainty. And that means that our displacement vector will become a vector with a confidence ellipse around it. That is what you see over here. So if our uncertainty in the alignment of the frame is poor, then these angles would become bigger. So, and this brings me to something which is very, very interesting, I think, because now we go from locally a two-dimensional frame. So we have here, it's TLN, so it is transversal longitudinal normal, but the longitudinal component is 0. So here we have actually only the transversal and the normal component that we're estimating. So locally it's two-dimensional. But if we are now going to apply this over many areas in the area, then it's going to become globally three-dimensional. So we call this 2D local, 3D global. And here you can see what that means. So here you see, again, a subsidence bowl somewhere. There's salt mining going on here, but the purpose doesn't really matter that much. And what you see is that we identified this kind of bullseye pattern, A, B, C, D, E, and then 1 to 12 in terms of segments. And here we bluntly took all the scatterers within one of those frames to estimate the motion of that particular region of uniform motion. So here the number A12 is bigger, and the number D1, for example, is a bit smaller. And in the center of each of those frames, you see a blue vector and a red vector. The blue vector is the normal component. Here, because it's a subsidence bowl, it's actually very close to vertical. But to stick to our terminology, we call it the normal component. And the transversal component is now actually a component which has an east and a north element in it. So these are the red lines that you see. So to compare on one end here we have this result. On the other hand, if we would just do the east-west and the vertical component, then we get a totally different perspective. Of course, here we're doing it in colors and here in vectors, but you would not see anything about the red arrows over here on the right image. Now, if you then zoom in, then you can see and appreciate also the uncertainty element in it. So we're now zooming into the middle part, and now we show the confidence ellipses over here. And this is very, very interesting because, okay, so the vertical first is in blue, and the confidence region is an error bar. And so here we see that this is very significant because the error bar is small and the length of the vector is very big. So all the vertical components estimated here in this region are very significant. And the red part, you can see, for example, that the one that I'm pointing out now, here we have a pretty long red arrow and a very small confidence ellipse. This means, and this is a 2 sigma confidence ellipse, so 95% of all the solutions falls within this ellipse. So actually, this is also a significant observation. So many of those areas, even if they're a little bit, also have a north-south component, they are still useful and they are still valid observations. Not all of them. For example, the one here in the middle, here you can see the red vector, which actually makes sense if you look at the direction. But in fact, the confidence ellipse is so large that you would never rely only on this observation. So we're not doing any magic. We're not creating north-south sensitivity because, I mean, if the sensitivity is not there, we cannot introduce it. But what we can do is we can estimate the quality of the observation and translate that to the quality in the three-dimensional estimates. And our line of reasoning is that this makes a lot of sense because now if you interpret this, and you have the confidence regions with it, you can make a reasonable guess. You can interpret this. If you would not have the confidence ellipses and you would look at these vectors, then yeah, you would take them. Basically, you're using them as deterministic variates, and then you would make definitely the wrong interpretation. Now, I'll give an example. So here we have in the upper left and the upper right figure, we have a fault, and along this fault, on one side of the fault, there is groundwater, which is upheaving. And in the line of sight, we see the differences in figure A and B. And what is interesting to note is that the blue part at the upper part of the red line here, from the descending orbit, it is on the upper part. On the ascending orbit, you don't see it at the upper part, you only see it in the southern part. And this is due to the viewing geometry and due to the fact that there is horizontal motion. Now, if you would convert this to the east up, like we traditionally is done, so then the up component is indicated over here with these vectors. The east component is orientated like this. And here also the colors indicate the east component. Now I'm going to change the A and B figure now by our approach, the TLN frame approach. And now you see that the normal component and the up component is more or less the same, but we do have error bars now here. But the transversal component here, orthogonal to the fault, they make a lot more sense, obviously, right? So even if you look at the colors, you completely miss information here. And this is very well possible if we know what we're interested in, if we have contextual information. So in this case, we would need to know that there is a fault and that we are expecting something here around this fault. Okay, so this is a whole set of work, and if you'd like to know more about it, there are 2 papers that you can see over here. One is basically a treatise on the INSAR geometry. So we went through the whole set of equations in depth and said, okay, well, how does it relate? What can we measure and what not? And the other one is the strap down approach that I was explaining, which you see over here. So the conclusions here is that obviously, as we know, INSAR is only sensitive to the projection of the 3-dimensional displacement vector onto the line of sight of the satellite. So we cannot measure vertical, but we measure the projection of the displacement onto the vertical, if you're interested in that. So if you have 2 observations, you still have an underdetermined problem with an infinite amount of possible solutions along the null line. So this concept of the null line is an important thing. Third, if you have some kind of information, or if you know what you're doing and why you're doing it, and our argument is that in most cases, if you have AAA products, application aware and aligned, you know what you're interested in, so you don't do it in the blind. That means use the contextual information that is there. So if you know that there's a mountain, there's a slope downward, and you know that there is gravity on the planet, then it makes sense to take that information into account. And if you do it explicitly, if you also state that that information is taken into account, then it's also refutable. People can object or come up with criticism, which is good because that brings us further. So the strap-down approach is a straightforward physics-based solution to the underdetermination problem, resulting in a physically more meaningful result. And the final thing here is that the traditional vector-based visualizations, like you see here on the lower right, which were very, very common in triangulation in geodetic networks, for example, they may be much more informative than the traditional colored dots type of figures that we are so used to look at in the INSAR community, simply because these colored dots do not have error bars. You cannot express the quality there. And the vectors, with vectors, we can have the confidence ellipses. Okay, so this was my second part. I see that I have 10 minutes before the end of this scheduled 2-hour block. So I'm going to stop here, and I'm going to see in the chat whether there are some questions coming in, and then I can still address them. Thank you at least for